Let's start this session with some more concepts in the advanced encryption. The security measure or ciphering starts with the first step, that is the substitution. For transforming, we use the method of sub-byte transformation. For E I have, how do I transform is 4 will be in a row. Hello students, welcome to the next session of network security. I'm Dr. Soumyashri from Department of Computer Science, Vidhyaashram College. Let's start this session with some more concepts in the advanced encryption standard. A block cipher which is improvised and is proposed by NIST with the intention of coming over the disadvantage of the DES, that is data encryption standard. Let's continue with the concept of advanced encryption standard. In this advanced encryption standard, the security will be provided by using 4 types of transformations. Okay, which is the transformations is, one is, first step is substitution, second step is permutation, third is mixing, and fourth is the key adding. Okay, 4 steps will be followed in AES, which gives you the security over the concepts or security over the data that is passing over a network. Okay, the security will be starting in AES. The security measure or ciphering starts with the first step, that is the substitution. This is what, but in DES, the first step is the permutation, isn't it? We have to initially permutate and final permutation must be done. Whereas in AES, the step starts with substitution. The procedure or the process will start with substituting the cipher text or the bits that are represented in the byte form will be substituted by some other characters. How they are going to do that? We know about the different substitution ciphers, is it not? With the substitution cipher, right? The AES, in some stage DES also uses the substitution, but AES in the initial step itself uses the substitution method. Okay, it uses 2 invertible transformations. It is transforming the text from one form to another form. Okay, the first thing is, the first step that we follow is, procedure is called as the sub bytes, getting the sub bytes from the normal byte that we use. All right, the first transformation step is called as sub bytes. Getting the sub bytes from the normal message is used at the encryption side. This is all about how to encrypt it. As we know, if we know the procedure of encryption, you can easily decrypt it, because decryption is exactly inverse of the encryption, isn't it? It is done at the encryption side to substitute a byte. When you want to substitute a byte, we interpret byte as the hexadecimal digit. Okay, we divide the byte, which is of 8 bits, into 4 bits. Each set of 4 bits is considered for an hexadecimal digit, isn't it? What is the representation of hexadecimal? It is 2 to the power of 4, that is 16, isn't it? We have 16 numbers. That means number of 4 combinations, 4 bits will be carried out for a hexadecimal number. So for the understanding of the transformation, the word a byte will be replaced like this. Suppose if you have this byte is divided into part of 2 bytes, where each byte is represented in the form of a hexadecimal digit, whereas 0011 represents 3 and 1001 represents 93. The whole byte will be replaced by 93. That means the 8 bits will be replaced by only 2 numbers. Okay, we have 8 numbers in this. So memory space and representation will be easier in case of hexadecimal. For this intention, the sub-byte uses the hexadecimal representation for each byte in the message or in the plain text. Okay, the sub-bytes operation that we follow in the AES involves 16 independent byte-to-byte transformation. It is not transformed at a stretch. Instead, it involves 16 independent transformations. If you have how many bytes you have, there will be 16 different transformations that can happen over a byte. Okay. How many bytes we use is 128 bits, isn't it? If you form it to the bytes by 8, what you will get? You will get 8 ones are 8, 8 6 are 48. That means you can transform 128 bits of key into or 128 bits of data or plain text into 16 bytes. In these 16 bytes are transformed to some other byte in 16 independent transformation step. Alright, for transforming, we use the method of sub-byte transformation. How do you do this? You know about the substitution cipher that we used or that we have studied in the substitution cipher concept, isn't it? So what are the substitution cipher concepts we have studied is the additive cipher, multiplicative cipher, affine cipher, auto key cipher, then playfair cipher, isn't it? So in that we have the playfair cipher. What is the concept of playfair cipher is? The codes or the plain text characters are represented as in the form of a matrix, isn't it? Using the matrix, you can get the substitution characters for the alphabets that we use in the message, is it not? If you are not familiar or you have forgotten it, just view the previous presentation, previous video, so you can get to know what is playfair cipher. Same concept of playfair cipher is used in the sub-bytes transformation. We have a step of sub-bytes where we use the matrix representation for the bytes. So 16 cells will be there. Each cell represents a byte in the form of a hexadecimal representation. Okay, where you have to match the column and the row to get a new transformed byte. Like we use the row, corresponding row of the first bit. So hexadecimal digit will have, like if we have 8E, this 8 will be considered as row and E represents the column value in the matrix, represents the row value and the column value in the matrix. In this, so we have the 8E, 8 is represented as row. We have to check for the row value 8 and the column value E. When this both values intersect with each other, this will be the new value that we can obtain. Okay, here we have, if the value in this hexadecimal byte in this cell, if it is CD, we have A and B. A is row value and B is column value. When A and B both intersect at a cell, that cell value is used to transform or substitute the AB with CD. So this will be stored or taken as a new transformed byte. Okay, this is the sub-byte transformation. We use the sub-byte transformation table to do this. Okay, here we have the sub-byte transformation 1. If I say we have a byte 4E base 16, 4E I have, how do I transform is 4 will be in a row, 4th row and E column. So we have to intersect these values. So this is E and 4. They intersect with this cell. Therefore, the alphabet or the byte 4E representing the alpha hexadecimal number will be transformed to 2F of 16. So this is how you can transform. You know about the rules of the Playfair cipher, is it not? How do you perform the Playfair cipher? Intersecting the row and the column values, isn't it? So we have the 4E representing 4 as the row and E as the column gives you 2F with the base 16. Sometimes the byte representation may be a little bit confusing. How it is confusing is, suppose if you take two values, 5A and 5B. We have two bytes, 5A and 5B. But the thing is, in 2 bytes, 5A and 5B, we have only half a byte of differentiation, isn't it? So it is differentiating by only half the bit, isn't half the byte, or in only 4 bits, isn't it? Otherwise, it is same. 5, row value is 5, only cell value, column value is differing. Only this half byte is differing from each other, only by one value. But when you transform these values, 5A and 5B gives 4 separate bytes, like 5A and 5B, even though they are differing from only one bit, 4 bits, the transformation differs them in all the 8 bits. 5A will be transformed or substituted by BE, whereas 5B is substituted by 3, 9. So we have transformation procedure where sometimes the input will be confusing, but when you transform it using the table, substitution table, you will get all new kind of transformation data. Okay, so this is the transformation table that is used in the sub-byte procedure. This is the continuation of the 16 numbers from 0 to F row wise and 0 to F column wise. You can use this table for transforming all the 16 bytes. All the 16 bytes uses the same transformation table. There is no difference. There is no more substitution tables. Whereas in DES, we use 8 separate substitution boxes, isn't it? To substitute 16 bytes at a stretch, is it not? So we use 8 substitution boxes to replace the bytes. But the AES uses only one transformation table to transform all the 16 bytes of data. All right. Along with this, we have a inverse of sub bytes, that is used when there is a decryption process. Decryption process, from original transformation, we have to take it back to the plain text, isn't it? So plain text representation is in the hexadecimal format. So we use a procedure which is the reverse of the sub bytes, which is called as the invert sub bytes or INV sub bytes. It is short form of inverse sub bytes. So this is a function we use in the AES algorithm. All right. This is the invert sub bytes transformation table. One thing we need to remember in the substitution of the sub bytes and the invert sub bytes, both are reverse in nature. All right. Suppose if you have taken 5A and 5B in the sub bytes, what was the answer? We got it is the BE and 39, is it not? So BE and 39, BE and 39. When you look at the invert sub bytes table, if you want to transform BE and 39, what is the transformation result you get? First we shall take BE, B in the row value. So we have B in the row value and E. So which is the E column here? This is the E column. Last but not least is the, it is not the last, one column before the last, E and B. So here we have the B and the row and the column E, isn't it? So to which it is going to generate is again the 5A. It is going to generate 5A. From 5A and 5B, we got BE and 39. From BE, again we are getting 5A. Whereas, if you check for 39, so 39 will be here, third row and ninth column. So where it is intersecting? 5B. So this is getting for 5B. Now we have 5B. This is followed in, sub bytes is followed in encryption method, whereas invert sub byte is used in decryption procedure. Okay. Since we need both the encryption and the decryption procedure, we have to use the sub byte and the invert sub byte tables, transformation tables. Alright. So this is about the transformation. Now let's take another example, 7.2 or example from the textbook that has been prescribed. So we have a figure which shows how a state is transformed using the sub bytes transformation. How do you transform a set of bytes in a matrix or state? So state uses the 4x4 matrix, isn't it? You know about the block and the state. We used the data units that we used in the previous representation or previous session, isn't it? So we used block and state. So state uses 4x4 matrix, isn't it? So this diagram shows how does the transformation from one state to another state happens. This is the state with the plain text representation. This number represents the plain text message. Okay. It creates the transformation. This uses the sub byte, whereas this matrix uses the invert sub byte to get it back the plain text. If you have the state with 4x4 matrix, this representation will be of hexadecimal representation of original message. This will be used by the sub byte procedure or function to transform it to the cipher matrix. This represents the ciphertext matrix. So from ciphertext to plain text, transformation procedure uses the invert sub byte concept or invert sub byte function to convert this to the plain text. Okay. So here it is shown in the example diagram. We have the transformation using the GF 2 to the power of 8 field. GF stands for Galois field, which was used to transformation using the 2 to the power of 8 irreducible polynomial field. What is irreducible polynomial field? You can refer to any internet concept where it says that it is not reduced polynomially, but it is reduced with the values according to the reducible form. Okay, here we have the Aes defines the transformation algebraically using the gallows field or GF's 2 to the power of 8 field with the irreducible polynomials like x to the power of 8 starts with x to the power of 8 as it is represented from 2 to the power of 8. So it is x to the power of 8 plus x to the power of 4 plus x to the power of 3. Next comes is not the x to the power of 2. Instead it will be x plus 1. We use the irreducible polynomial to define the transformation in the advanced encryption standard. So this can be as shown in this diagram. We use the substitution table matrix with row and column with x and y values to the power of -1, that is it must be denominator and has been taken for the numerator, and inverse sub byte will reverse or find the complement of this. Okay, that is x to the power of -1 into d XOR y. We perform the XOR operation on the x and y representation. Okay, so d plus y, d XOR y to the power of -1, which can be deduced to this representation. Okay, so what is the meaning of this is the sub-byte procedure and invert sub-byte transformations are inverse of each other. Whatever the sub-byte is doing, exactly the inverse will be or reverse will be done by the inverse sub-byte procedure. Alright, so we have the process of the sub-bytes and invert sub-byte processes. Here we have the state matrix which will be given as S of RC, that is substitution table with row and column. It will be inversed and is transformed into from byte to matrix. Okay, so here we have the matrix values and the column values. Okay, and now we have the D equals C plus Y, that is ciphertext plus Y. So ciphertext is represented like this, plus Y will be made from matrix, it is converted to byte and in the form of a matrix and is changed into state. Whereas the invert sub byte performs the decryption. This is a decryption process, whereas this is a encryption process. Okay, we have encryption and decryption process which represent the normal and the reverse process. This uses the sub byte, whereas this uses the invert sub byte procedures. Okay. The next example we can take is how the byte 0C, we have the 0C, is transformed to FE. We are transforming the byte 0C to FE by the sub byte routine and transformed back to 0C by the invert sub byte routine. What are the procedures we follow for this is, we take multiplicative inverse of 0C in GF 2 to the power of 8 field. We take the inverse. The answer is B0. We get the value B0, which you can represent as B stands for 11, isn't it? So 11 can be represented as 1011. 1011 and 0 is, as you are already familiar, it is 0000. Now we have 4 first half byte representation and 4 bits of other half byte representation. So B0 can be represented as 1011 plus 0000. Now, you'll get the matrix X. Multiplying matrix X by this matrix having the transformation table represented as a matrix results in C equals, we get the 0C, C equals 1001 and 1101. So we have the multiplicative inverse we use and find out the C value. Okay, in the sub-byte transformation, we find the C in the procedure. The result of XOR operation, we include the XOR operation which has the value D with the procedure 4 ones and 11111110, which is FE in hexadecimal. So this is how you can get the transformation from 0C to FE. Next is the procedure of invert sub byte. The result of XOR operation in C is 1001, 1101. So the result of multiplying by matrix X inverse, so X inverse will be used, is 1101, 0000, which is represented as B0. So which is the multiplicative inverse generated by the invert sub byte procedure. We have the B0 which is inverse of 0C. Okay, we get the encryption and the decryption procedures in this concept. Okay, now we have the algorithm that can be used for the sub bytes transformation. Here we have the function sub bytes with an input yes. It is the substitution matrix we get from row 0 to 3, from column 0 to 3, we get the R and row and column value. Now we have the byte representation, byte input for the sub byte sub function. Okay, here we use the inverse of byte, okay, multiplicative inverse in GF 2 to the power of 8 with inverse of 00 to be 00. Wherever you go, the inverse, multiplicative inverse of 00 is always 00, isn't it? So we have to take the matrix of byte representation A comma B for I 0 to 7. Okay, 8 bits 0 to 7. So each bit is applied with an XOR operation to get the transformation, okay, from one representation to another representation. Once the transformation is over, so the byte will be again represented with the matrix and we get the matrix representation in the form of a state. This is about how you can transform using the substitution tables. We use the substitution tables instead of substitution box. In DES, what we do is we use to have 8 different substitution boxes to get the substitution of 32 bits at a stretch, isn't it? And we get 4 outputs from each of the substitution box. So that is where the DES has the advantage. At a stretch, you can transform the different bits. But in AES, we use 128 bits of input data as well as round keep, isn't it? To use the substitution boxes, it will take so much of input, but the limit for substitution box is only 6 inputs and 4 outputs. So what is the solution is, instead of using the substitution box, we can use the substitution transformation table. What does the transformation table will do is, it will transform like in Playfair cipher that we do. It will represent the bytes in the form of a matrix, and the conversion from matrix to bytes will be taken once the transformation happens. How does the transformation is going to do is by taking the row value and the column value. When they intersect with each other, there will be the intersection cell which can be used to get the transformation matrix using the sub-byte procedure. Once it is over, for decryption, you can use the invert sub byte table, transformation table, which converts from the substituted or transformed code to the normal byte representation. This is how you can transform in encryption as well as in decryption. In the next step or in the next session, I am going to explain you about the key expansion in the AES. That is the next step of transformation in the AES. Alright. Thank you.